Welcome to my lecture series about bad science in the news. In this lecture, I will attempt to answer the question, why does bad science go public? I'd like to start by talking about the general process of publishing when it comes to scientific research and also the news. So in terms of publishing science, there are researchers who conduct science and hope that their research gets published. Getting published is kind of an important thing to scientists and researchers. Of course, researchers, one of the hurdles they face in getting published is convincing a journal editor that the work they've done is important and also fits with the orientation of the journal. The journal editors make those decisions in part based on what the publisher wants, what type of research typically appears in that journal, how prominent the research is, what types of theoretical orientations are used. And so what the publisher wants affects what the journal editors, at least affects somewhat what the journal editors will send out for peer review, and that affects what types of work researchers can publish. Similar process affects news publishing, where there are journalists who cover events and hope to see their coverage appearing in newspapers or on television or discussed in the radio. Of course, journalists need to respond to the needs of news editors, and those news editors are responding to the orientations of the news outlets or the news organizations where they work. And so there are these two spheres of scientific publishing and news publishing, and where they intersect is very often where the public engages with science information. Now, I'd like to talk a little bit more first about the process of scientific publication, starting with a brief discussion about what motivates scientists. There's been research on this subject, and a number of different factors motivate researchers to do their work. For example, to get research funding or support. So good science can get more funding for researchers to do even more good science. They're also motivated to have impactful findings. It feels good if research has a positive impact on the world. That motivates researchers. Some researchers are just satisfying personal curiosity. Their motivation is highly intrinsic. Researchers are also motivated to increase their income. For a lot of researchers, publishing and doing science is part of their job, and of course it becomes linked with their salary. And then kind of related to having an impact on the world, some scientists are motivated by gaining recognition, gaining prestige, gaining acclaim. So these are all factors that can affect why scientists do their work. But is it necessarily affecting what actually gets published? I would say, yeah, for the most part, it is. I would say most research is driven by good motives, and researchers follow robust scientific principles in conducting their work. But there are some issues that arise in terms of what gets published. Perhaps you've heard of the file drawer effect. Sometimes researchers will find that none of their hypotheses are supported. They don't have any statistically significant effects. And they might feel discouraged about that and not even bother sending this study out for peer review. They might just put it in the file drawer. Sometimes, even if it goes out for peer review, the study might get rejected by the journal because it didn't really show anything. Now, that's actually a problem when it comes to using research to inform important decisions. So maybe you've heard of the concept of evidence-based medicine. The idea is that medical practice should be based on the best available evidence from scientific research. And very often, these evidence-based recommendations come from meta-analyses. Meta-analyses collect all of the studies that have been done on a topic and identify if there is a consistent pattern, consistent findings among all those studies. Of course, if a lot of studies are being excluded because they didn't find any significant effects, well, then they aren't going to appear in the meta-analyses. If they were included in the meta-analyses, maybe the medical recommendations would be different. This is a real issue, and scientists are aware of it, and they do what they can to address this potential source of publication bias, especially when conducting meta-analyses. Another problem that arises in publication is an issue of Pea hacking. And I'm going to give you an example of Pea hacking. I think this is the best way to explain it. So say that you conduct a survey of 1,000 people and you ask them 15 questions that you drew at random from all the known survey questions in the universe. In theory, there shouldn't be any reason to expect that any two variables would relate to each other. And of those 15 random variables, you can evaluate 105 possible correlation coefficients, the relationship between any two variables. By the way, how did I get 105? Here's a quick little math lesson. So if you have 15 variables, that represents k, and the number of possible correlations is k times k minus 1 divided by 2. Here it would be 15 times 14, which is 210, and then divide that by 2, and you get 105. All right, so you have these 105 possible correlations. You would expect to find, even though these are random correlations, you would expect to find that 5 of them are statistically significant, assuming the traditional threshold of p equals 0.05. P equals 0.05 refers to the type 1 error probability, and it's basically p is the probability of observing that two variables are related, or the probability of observing an effect when there is no effect. So essentially here this is saying that researchers accept a 5% chance of observing effects when there really is no effect. That's type 1 error. All right, so these 15 random variables, I find 5 significant correlations, and I use those significant correlations to develop a model or theory, and I don't report any of the non-significant correlations. That's Pea hacking. I'm basically finding correlations that happened due to random chance and attributing some sort of meaning to that. This is a spurious effect, essentially, and there's some interesting spurious effects that actually happen. This I took from tylervigan.com. The website contains a number of entertaining spurious relationships that have been found. So this shows that from 2000 to 2009, per capita cheese consumption is very strongly correlated with the number of people who died by becoming tangled in their bed sheets. We could all dig around in databases and find similar patterns if we dig around enough and look at narrow ranges of time. And I could maybe come up with a theory that maybe the chemicals in cheese somehow cause people to toss and turn more in their sleep, therefore they are more likely to get tangled in their bed sheets. So eating cheese causes people to die by getting tangled in their bed sheets, right? That's Pea hacking there. And of course, I don't think that theory is correct. It might be, but I would say there's an exceedingly high probability that my theory is completely wrong, and this is just a random correlation that happened to be noticed. All right, so that's the issue of Pea hacking. And then there's this issue of publishing what's important and sexy. There's a lot of basic research that doesn't really stand out, that isn't going to be important to the news media, that isn't going to be important to the public, that still might be important for research, but it might not get published because it's not sexy. Sexy research tends to get published more often. Now, I found a pretty funny comic that exemplifies this issue of, well, Pea hacking and the drive for publishing sexy research and the file drawer effect, making sure that findings are significant. I found a funny comic on PhD comics, and the first pane presents the scientific method. This is a condensed version of the scientific method. So researchers observe a phenomenon. They formulate hypotheses on the basis of that observation. Then they test the hypotheses. If they find the hypotheses aren't supported, they go back to the literature, go back to the drawing board, and see if maybe they missed some important literature. They refine their hypotheses, they test them again. Eventually they find support for hypotheses that are consistent with the phenomenon they observed and consistent with prior research that's been studied. Over time, a collection of repeated findings can be used as the basis of forming a theory or a theoretical model. So this is a condensed form of the scientific method. In panel 2 of the comic, there's the actual method. Now, if you watched my recorded lecture about the scientific method, I talk about the wheel of inquiry, and it's an expanded version of the scientific method, of the wheel of science, that gives a more accurate representation about how scientists actually do their work. This is a slightly different actual method, and it's kind of tongue-in-cheek, but it's not entirely tongue-in-cheek. So the actual method is start by making up a theory based on what funding agencies want. Step 1. Step 2, design the easiest possible way to show that theory or to show some of the relationships that it suggests. Step 3, publish a paper, but since it was never a theory in the first place, just a crude hypothesis, you rename it a hypothesis, and on the way to publication, you make sure that the theory fits the data. Now, this is completely backwards. You shouldn't normally tweak a theory to match the data. You make observations, you collect data to validate a theory. If the data don't match the theory, you say you don't have support for the theory. You don't revise the theory. You don't do an overhaul. And then, because these results probably came out of Pea Hacking, because this theory probably came out of Pea Hacking, it won't stand up to any sort of replication, but you defend it anyway because it's your theory, right? Okay, so this is kind of tongue-in-cheek, but some researchers probably do this because they're really, they're pressurized to publish statistically significant, sexy research, right? And so then they engage in some Pea Hacking and come out with a potentially compelling study that's complete bunk. All right, so those are some of the issues facing science publication. Let's talk a little bit about news publication. And I'd like to start by talking about some principles that guide news reporting. So if you've taken a journalism class, you would have learned about some ethical principles, and these are pretty straightforward and intuitive. Like truth and accuracy, journalists should represent the world in the news they report in a truthful way and cover the details accurately. They should be independent. They shouldn't be representing special interests in their reporting. They should be accountable. When they make a mistake, when they report about something incorrectly, they should correct it. They should own up to their mistake. There should be transparency in their reporting. They should engage in non-maleficence. This means do no harm, at least collectively. When you report on some facet of the world or of society, it should have a cumulative or net benefit for the world. And then finally, there should be balance in reporting. The report shouldn't be one-sided. Of course, balance can be problematic. If you watched my lecture about the autism vaccine link, balanced reporting actually leads people away from belief in the scientific consensus and away from the scientific truth. I'd like to talk a little bit more about balance and balanced reporting because in that other lecture I presented the results of a laboratory experiment. It wasn't a real world study of news stories. They were manipulations created for the experiment. Different news stories presenting the autism vaccine link in a balanced or one-sided way, right? But does this type of reporting actually occur? Well, there was a study by Boykoff in 2008 looking at US television coverage of climate change over the decade from 1995 to 2004. And what was found is that, well, about 28% focused on there being significant human causes, a fairly one-sided argument that humans are a major factor in climate change. Only 3%, and this is good, only 3% said there are negligible human causes. That was the emphasis in that small minority of the reports. But almost 70% had balanced reporting, saying that some scientists say humans are causing climate change, other people say humans are not causing climate change, it's due to natural patterns. The problem, as I addressed in my other lecture about the autism vaccine link, is that balanced reporting really affects people's beliefs about science, and it's problematic. So 70% of those stories presenting balanced perspectives actually was more detrimental than the 3% that said humans have a negligible impact. At least that's what some laboratory experiments would suggest. So balanced reporting is problematic. Okay, so those were the ethical values guiding news reporting, but then there's also this concept of newsworthiness. Journalists want to publish, and newspapers want to publish, and editors want to publish what is newsworthy. And there are 5 factors affecting newsworthiness. One is timeliness. It should be a current event, something that's happening more or less now. There should be proximity. It should be geographically or physically close to the people who are reading the news. It should be something in the community or something that is of geographical relevance to them. That makes it more newsworthy. Controversy is newsworthy, and this is kind of a problem when talking about scientific controversies, when if you actually speak to the scientific community, there's really only one side. And presenting the controversy and building on the controversy actually creates problems in discussing these issues in public. News is newsworthy if there's human interest, if people can see the relevance to them as human beings, that the issues covered in the news are things that affect humans. And then speaking of relevance, the information encountered in news should be relevant to the decisions that people make. Now, if we're talking about the autism vaccine link and there's uncertainty about that link based on balanced coverage of the issue, well, it's going to affect people's decisions about whether or not vaccination is a good thing. They'll see the relevance of that information to their decisions, but then they'll be less able to make a decision. Or in the context of human versus natural causes of climate change, that can affect people's voting behaviors. The information is relevant to their voting behaviors, and that can have negative consequences if the science is not reported well in the news. All right, so that was the 2 spheres of scientific publishing and news publishing and where they intersect. It affects what the public understands about scientific issues, because so much of what people learn about science and about health and about the environment isn't from direct experience, but it's from what they learn through the media. Sometimes that information they encounter is, well, it's bad science. If you are curious about any of the papers I cited, of course the links are in the description. Thanks for watching.